Hey guys, we're going to talk about inverse trig and calculus, which is a good thing to talk about because the inverse trig functions and their derivatives are the kind of functions where you look at them and you just say to yourself, those are really ugly functions. I'll just memorize their formulas instead. So we'll be going over hopefully some reasoning behind them. And before we find the derivatives of the inverse trig functions, let's just think about what the derivative of an inverse function means in general. So you'll have f of x, and then you'll have f inverse of x. And those two are defined so that f of f inverse of x equals x. So let's say f of x is just some function. Maybe it looks like that. And then f inverse of x is just like f of x reflected over the line y equals x. And so that would look something like that. And one cool thing about the derivative of inverse functions is that they're reciprocals of each other. So here's an example. If you have f of x, let's say the derivative at this point is just it's 0. It's a horizontal line. And then you go to the equivalent point on the inverse function. It's a vertical line. And it'll be like that for any point. So like the derivative at this point looks like it's about 1. And then the derivative at that point here is also 1. Or here you have another slope of 0, and then right here you have another vertical slope. So you could say that the slope of an inverse function is 1 over the function's derivative of the inverse function. And using the definition we have for functions and inverse functions above, we should be able to check to see if that's true. So let's go ahead and do that. Let's take this and let's derive both sides. So f prime of f inverse of x, and then we have to multiply by the antiderivative, times f inverse prime of x, and this guy's what we're looking for. This is what we're trying to solve for, equals the derivative of x, so that's just 1. So then since we're trying to solve for f inverse prime of x, let's divide both sides by this. So we'll just move this over here. And we'll see that what we figured intuitively was correct. So I'll box this definition, this formula, and I'll put that in the corner. And we'll use that to solve some inverse trig functions, although there are other ways we'll use too. So let's start with sine inverse of x. Sine inverse of x. So the derivative of that would be equal to 1 over. Alright, well, what's the derivative of sine? That's cosine. 1 over cosine of sine inverse of x. And now is when we start drawing triangles. So there's a triangle. Let's label an angle theta. So sine inverse of x is an angle whose sine is x. So opposite over hypotenuse, x over 1. And then cosine of that is adjacent over hypotenuse. So we have to find the adjacent. Square root of 1 squared minus x squared. So then cosine is just this. So then we get the derivative of sine inverse of x is 1 over square root of 1 minus x squared. So then next we'll look at inverse tangent of x, and we'll solve it using a different method. So tangent y equals tangent inverse of x. So we want to find the derivative of tangent inverse of x, but we don't really know any methods to derive tangent inverse of x straight up. So why don't we rewrite it in a way of functions that we can solve? So let's take the tangent of both sides. Tangent of y equals tangent of inverse tangent of x equals x. So now we can use implicit differentiation. So let's do that. What's the derivative of tangent of y? That's secant of y times secant squared of y dy, and then that equals the derivative of x, so that's dx. Now we're trying to find dy dx, so let's divide both sides by dx, dy dx, and then multiply both sides by cosine squared y. So then the derivative we're looking for equals cosine squared of y, and up here we can see that y is tangent inverse of x. So we're looking for cosine squared of tangent inverse of x. So now we need to draw some more triangles. Tangent inverse of x. So here's a second triangle, and here's a second angle, theta. So tangent inverse of x is an angle whose tangent is x. So then tangent is opposite over adjacent, x over 1. So then cosine squared of that. Well, cosine is adjacent over hypotenuse, so we need to find the hypotenuse. That's 1 squared plus x squared plus x squared. So then what we get here is 1 over square root of 1 plus x squared, and then that squared. So we'd get the derivative of tangent inverse of x equals 1 over square root of 1 plus x squared squared. So 1 over 1 plus x squared. And then there's just one more function we need to find the derivative of, and that's secant inverse of x. And we could do that either way, but for this example we'll do that using this guy, because, well, no reason. That's just, we'll just do it that way. OneNote's giving me problems. Secant inverse prime of x equals 1 over, what's the derivative of secant? That's secant tangent. So 1 over secant of secant inverse of x times tangent of secant inverse of x, of secant inverse of x. So the reason I like doing it this way is because we get this little fella here, secant of secant inverse of x. So it's just 1 over x tangent secant inverse of x. So you know the drill. We need a triangle and an angle. And secant inverse of x is an angle whose secant is x. So secant is hypotenuse over adjacent, so x over 1. And then we need the tangent of that, so opposite over adjacent. We need this side. So that's the square root of x squared minus 1. So then tangent is this over opposite over adjacent. So then we get secant inverse prime of x equals 1 over x square root of x squared minus 1. And box. And now you might be wondering, well, what about the other 3 trig functions? Those aren't all the trig functions that there are. And I'll explain why we don't have to worry about them. So there's the 3 I haven't mentioned are cosine inverse of x, cotangent inverse of x, and cosecant inverse of x. And the reason you don't really need to solve these the same way you did the others is you can rewrite, okay, well, cosine and sine are the same function, just shifted over pi over 2. So here you have cosine, and here you have sine. So you can rewrite cosine inverse of x as sine inverse of pi over 2 minus x. And then to find the derivative of cosine inverse of x, you could just find the derivative of this, which surely you'll agree it's the same as the derivative of sine of inverse of x times the inner derivative, which is just negative 1. And then same thing for cotangent inverse. That's simply tangent inverse times pi over 2 minus x. So it's the same times the inner derivative times negative 1. And same thing for cosecant. And that is all. Hopefully you have a better understanding of why inverse triggers are the way they are.